I'd like to welcome everybody to the BSL colloquium. Today we have Curtis Baden and Roland Bergman will give the introduction.
Yes, welcome to the first in-person BSL seminar since March 2020. It's very exciting. I'm excited to welcome back Curtis. As some of you may know, he's actually a product of our department. He was an undergraduate student here, majoring in geology, graduated in 2013. Back then, he actually did some really cool research with David Shoestone, estimating exhumation rates using cosmogenic isotopes, beryllium-10, right?
Beryllium, yeah.
Yeah. And he was also our valedictorian, so a star student who then decided to move across the bay a year later in 2014 to do his PhD with George Hilly. And he's just about to wrap that up this year. And so with George, he has worked his primary project, which you will learn about today, really sort of integrating a wide array of observations over all timescales of how a mountain range deforms from the earthquake cycle timescale to the long-term geologic evolution, which I think is really, really cool research. So welcome back, Curtis. It was great to have you visit today and meet people, and I'm looking forward to your talk. Take it away.
Thanks, Roland, for that intro. It's great to be back in Berkeley and on this side of the bay. The talk that I'm about to show you represents about a decade's worth of work out of George Hilly, my advisor's group, as a late stage graduate student, much of what you're about to see is encompassed in my dissertation. And I've been working on this for quite a while. I haven't shared it with anybody for about 2 years, so I'm excited to share it with all of you today. Maybe if I click it. There we go. Okay, so from earthquakes to Earth structure, over short timescales, we observe that slip-along faults generate earthquakes, and continued plate motion in the presence of locked faults generates interseismic, largely elastic bending. And in the long term, we observe that these integrated deformations generate mountainous topography and rock uplift, other metrics that are recorded as inelastic deformation in the rock record and in the geologic record. So the question is, how do these largely elastic deformations that we observe and model with elasticity and viscoelasticity actually transform to these observations that we observe in the geologic record, which record demonstrably inelastic deformation? This very question has been identified as a grand challenge in many community white papers and planning documents, notably NSF, AGU, SCEC, and the USGS Hazards Program. From these questions, or rather from these documents and in this talk today, I'll hope to answer 3 primary research questions. So first, how does largely elastic deformation measured through geodesy transform into irrecoverable deformation observed in the rock record? Second, when and where does irrecoverable deformation actually occur during the seismic cycle, if at all? And third, how does the dynamic evolution of the fault boundary through time influence the distribution and magnitude of deformation that we observe today? In this talk, I will hope to convince you by the end that an elastic earthquake cycle augmented with elastoplastic failure in conjunction with an isostatic and erosional model work to actually transform these largely elastic deformations that we observe in the short term to these inelastic deformations that we observe on geologic scales. This talk has many moving parts, and so to keep us all together, I'm setting today's roadmap, and we'll regroup at the end of each one of these sections. But just to briefly walk through this now, we'll focus our study site in the Santa Cruz Mountains, which are just across the bay, and they are along the Santa Cruz coastline. We will then, from our observations of deformation and kinematic evolution of the Santa Cruz Mountains outlined in that section, jump to our hypotheses for how these deformation discrepancies might be resolved. We'll then walk through the modeling setup in which we'll first model the tectonics of the Santa Cruz Mountains with a finite element model. And then we'll couple that tectonic model with an Earth surface process model so that we can actually transform the tectonic deformations to observables that we observe in a variety of data sets. We'll finally test those model predictions with our observables to see how our hypotheses fare. We'll then model earthquake cycle deformation with this model to see how our finite element models might perform and how they predict, or when and where they predict deformation to occur coseismically and interseismically. And finally, we'll touch on related studies and future directions. So starting with the study site, the Santa Cruz Mountains, which are, here's Berkeley up in here and Stanford's down here. So they're right in our backyard, essentially. The Santa Cruz Mountains are actually bisected by the San Andreas Fault, and that's that bold red line. And the San Andreas Fault here accommodates about 15 to 20 millimeters per year of plate motion in this particular area. The Santa Cruz Mountains bend, which is a restraining bend in the Santa Cruz Mountains, works to convert horizontal to vertical velocities, or horizontal motions to vertical motions in the Santa Cruz Mountains bend by means of regional faults. This bend accommodates about a 12.5 degree change in strike in the San Andreas over the course of about 50 kilometers. And this is part of a larger bend structure that extends south to San Juan Bautista. The wealth of information and data in the Santa Cruz Mountains, that is interseismic velocities, marine terraces, erosion rates, rock uplift records, and apatite, uranium, thorium, helium, thermochronology, combined to make a robust data set that we are excited to explore. So starting first with our short-term records of deformation, earthquake cycle deformation, we're going to talk about observations in the Santa Cruz Mountains that occur over seconds, decades, centuries, and millennia, manifested in earthquakes, interseismic velocities, and paleoseismic slip rates. In the interseismic case, we observe that uplift and subsidence on the order of about 1 millimeter per year occur within the Santa Cruz Mountains, and that's that bottom panel. Interseismic elastic bending surrounding the San Andreas Fault also occurs, and we see that inverted slip rates for the San Andreas Fault in this area range between 15 and 18 millimeters per year. Coseismically, recent earthquakes are now somewhat part of earth science folklore just due to the massive amount of damage that they induced onto the San Francisco Bay Area and the infrastructure therein. So first we have the 1906 San Francisco earthquake, which had a rupture length of 475 kilometers and a maximum slip of almost 10 meters. And second, we have the 1989 more recent Loma Prieta earthquake with a rupture length of about 40 kilometers and a long fault slip of about 2.3 meters. And just to review the extents of those ruptures, the 1906 rupture ruptured all the way through Northern California, and the Loma Prieta rupture extent is minimal in comparison. Paleoseismic records are somewhat shaky in the Santa Cruz Mountains due to strike slip issues with trenching slight strike slip faults and resolving slip rates across them. However, the Filoli site in the north there has a slip rate of about 17 plus or minus 4 millimeters per year, which is consistent with the inverted geodetic rates. And recently, Kim Blizniak of San Jose State University reported that the Sanborn site there has a slip rate of about 25 plus or minus 3 millimeters per year. I'm excited to interface with Kim at a future date to talk about how her rates might fit into our model here. And she actually was a co-GSI for my structure class way back in the day. So with that suite of data, we'll now move back in the observational timescale here to tectonic geomorphology and landscape evolution, which records deformation on the order of tens to hundreds of thousands of years, recorded in beryllium-10 erosion rates, marine terrace uplift rates, and topography. Beryllium-10 erosion rates, which are measured through the concentration of beryllium-10 in river sands, where beryllium-10 concentration is inversely proportional to residence time and erosion rate, suggests that erosion rates are highest within the Santa Cruz Mountains, or within the bend rather, and then they decrease northward towards San Francisco. Persistent uplift along the coast of the Santa Cruz Mountains has preserved marine terraces during sea level high stands. And finally, we have the asymmetric topography surrounding the Santa Cruz Mountains. Now, notably, we note that Mount Loma Prieta, which is the highest peak in the range, occurs as a somewhat isolated and localized locus of uplift in the Bay Block there to the east of the San Andreas Fault. And that stands in contrast to the long elongate zone of topography west of the San Andreas Fault. And we note that this antisymmetric topography highlights the asymmetry in potential deformational styles over these timeframes and reveals something about the long-term kinematics regarding the deformation in the Santa Cruz Mountains. Now, if we take these metrics and we cast them in a long fault profile where distance is measured along this direction indicated by this blue arrow, and 0 starts here, which we're assuming is the beginning of the restraining bend right there, and distance is measured along this scale bar, and we convert these metrics into a profile metric. There we go, pardon me. We'll see that the following trends elucidate. First, we do indeed notice that the beryllium-10 erosion rates are highest in the southern Santa Cruz Mountains and decrease to the north, indicating that potentially uplift is highest within the bend and decays to the north. Uplift rates indicated by these marine terrace data, where on the X or the Y-axis here is coastal uplift rate, indicates that uplift is actually highest in the southern Santa Cruz Mountains here, again, as is consistent with potential uplift rates inferred from the erosion rates. And finally, we have these metrics for relief, which at this point are actually not particularly diagnostic, but we will use them later in our comparisons.
Are these the same age, the Pacific and the Bay Block?
That is a very interesting question, and we will touch on that in just a second, but not quite is the answer. The Bay Block has a bunch of Franciscan complex, serpentinites, ophiolitics, metasedimentary blocks. And the Pacific Block actually hosts the most complete Cenozoic section of geology in California. So it's a little bit younger and it's pretty geologically distinct.
Does it encompass the glaciation? Ice age?
It does not, I don't think. Well, actually, I mean, so I guess it would encompass multiple ice ages, but as far as the latitude of these sediments as the evolution of the San Andreas Fault brought these rocks northward, I'm not sure how much of the glacial record is actually recorded. All right, so stepping back to our final timescale here, which is over millions of years, we'll talk about apatite helium ages and rock uplift recorded in the geologic record. So first, we collected 15 bedrock uranium, thorium, helium samples in the Santa Cruz Mountains. And when we cast them along that bend profile metric as before, we'll note that in the Bay Block, ages hover around 4 million years here, and these outliers actually reside a little bit further from the San Andreas Fault along other thrust sequences in the Bay Block. The Pacific Block, in contrast, has young ages, which suggest high exhumation rates in the southern Santa Cruz Mountains, and then these increase to the north. I should also mention that these ages are roughly captured by the passage of apatite crystals through the 70°C isotherm, and we infer exhumational rates from these ages since a young age assumes that that crystal passed through 70°C not too long ago. We'll then take a look at the, also, I'd like to highlight the asymmetry in these ages across the San Andreas Fault, which more or less mirrors what we observe in the topography in terms of the asymmetry across the fault. Let's now take a look at the geologic record west of the San Andreas. So I'll first say that the heavily faulted and discontinuous Bay Block provides limited information on the evolution of the strike slip plate margin as we're concerned with it, just because there are few datums that you can reliably reconstruct and the structure is quite complicated. In contrast, west of the San Andreas Fault, the Santa Cruz Mountains host the complete section of Cenozoic geology in California, or the most complete section of Cenozoic geology in California. And if we actually look at that section, this actually records various temporal epochs during the evolution of the San Andreas strike slip plate margin, where a large portion of these sediments occupy the pre-San Andreas deposition. And these are represented in terms of deep sea turbidite fans and such. There are sequences that record basin deepening and transtension during San Andreas initiation between 15 and 25 million years ago. And then finally, there's the Santa Cruz Mountain bend initiation, which occurred about 4 million years ago, indicated by that leftmost red box. And we're going to focus most on that in particular. So when we dive into this section, we've explored this sequence with 18 structural cross sections and 40 apatite helium samples to quantify deformations since the formation of the San Andreas Fault, with particular eyes on deformations since Santa Cruz Mountain restraining bend activity since 4 million years. This is potentially the top topic of an entirely separate talk. So I will just summarize it here and say that long-term geologic and deformational histories influence the localization of recent deformation and uplift. And I'd be happy to talk about this with anybody who's interested at a later time. When we reconstruct that rock uplift field, reconstructed from those cross sections in apatite, uranium, thorium, helium data, we note the following trends in the rock uplift field. Notably, rock uplift is fairly minimal, close to the initiation of the restraining bend, and then rock uplift increases with distance to the north, where the arrows and hatched marks here note minimum values for rock uplift. With all of these data sets in our hands now, let's now walk through a kinematic model for the long-term formation of the Santa Cruz Mountains that might be consistent with the data sets that we've presented here. So in one sense, if we have a symmetric system or a symmetric bend and deformation about said bend is symmetric, we'll observe as we explore in this boundary element model, the deformation occurs symmetrically about the bend, and then displacements, which, high or warm colors denote high displacements or uplift, and cool colors denote low displacement, occur symmetrically about this restraining bend feature. On the other end, if we have an asymmetric bend deformation model where one of the plates is fixed to the restraining bend relative to the other, we might expect that deformation might localize within the bend adjacent to the fault in the fixed plate and advect into and through the restraining bend on the other plate. And if
these vertical motions?
These are vertical motions, yeah. And indeed, with this kinematic exploration, we observe that we do in fact see this trend elucidated. And so we infer based on our asymmetric age or apatite uranium, thorium, helium ages and topographic observations that we actually are dealing with an asymmetric bend model here. And we can move forward with that kinematic model to propose some hypotheses for how we might bridge short-term metrics of deformation with long-term metrics of deformation.
One question.
Yeah, of course.
Vertical, purely vertical, or should be a little bit dipping?
It should be dipping, and that's a really, really good question. It is not in our model, nor will it be in the rest of the models that we discussed, but there are really wonderful observations to suggest, or really compelling observations to suggest that the trace of that San Andreas may actually be dipping, especially in the Santa Cruz Mountains. And as was observed via seismic reflections in the Loma Prieta case. Yeah.
Because Loma Prieta didn't occur on San Andreas.
So there's a paper that suggests that the fault plane that was ruptured during Loma Prieta may have actually been a portion of the San Andreas. But for a very long time, the consensus was that it was an entirely separate fault, and this new paper maybe argues the other way on that.
Curtis, what's the difference between the two models? Is that the boundary condition different, or it's, how did you?
That's a great question. So it is a boundary condition difference. So the fault itself is held fixed and does not allow opening. And in the left case, half of the plate rate is applied to the lateral boundaries of each of the plates. And in the right case, it's the identical conditions for the fault, but the boundaries for the upper plate there are held fixed, and the full plate rate is prescribed to that lower block.
Thanks.
Yeah. Oh, another question?
Just the difference between those is a rigid body. How do you get asymmetry with just the difference in rigid body rotation or motions?
Excellent question. So in this case, the bend geometry itself is fixed.
Yeah.
And so the bend does not actually, so that bend is
I see.
because it's held fixed with respect to the boundary conditions of the upper fault. Or sorry, of the upper plate. So we'll now walk through our hypotheses that we can propose given these suite of observations that we've outlined here. So how is it that we actually bridge these disparate data sets that we've outlined? The null hypothesis might suggest that the purely elastic earthquake cycle produces deformation in Earth's crust that is consistent with observations of deformation spanning decades to millions of years. Our alternative hypothesis is that plastic failure of Earth's crust that develops during dominantly elastic earthquake cycles accrues through time during seismic cycles to produce the observed records of deformation. And then, of course, how do we actually test these hypotheses, given that we are starting with constitutive rules that we are hypothesizing? And with that, we'll move to the modeling portion of actually, modeling the tectonics of the Santa Cruz Mountains and then coupling those tectonics with Earth surface processes. So starting with our constitutive rule hypotheses and moving to the observations, we'll outline a model framework. We'll first model the SCM bend with tectonics, or SCM bend tectonics with finite elements. And then we'll convert those tectonic deformations to metrics that are similar to those which we observe using an analytical isostatic and Earth surface process model. So to outline our finite element model portion here, we start with the San Andreas fault geometry here, and we model this scenario in Abacus, which is a commercial finite element software package, in which we design a model that consists of two 3D blocks that are juxtaposed across a frictional contact surface with an initial fault geometry that is shown there in portion C. Note that the fault is vertical and that this initial condition is actually steeper than the observed San Andreas, such that it allows the fault trace to deform through time and shallow out as deformation accrues. We apply a far field displacement rate of 16.8 millimeters per year, which is consistent with the geodetically inferred fault slip rate along the San Andreas from 15 to 18 millimeters per year. We'll run the model for 4 million years, which is consistent with the timing of plate reorganization from 4 to 6 million years, which is what we suggest initiated restraining bend tectonic activity in this area. The preserved marine units, or the Purisub formation, limit the timing of uplift to about 4 million years because these units were previously submarine and they are no longer, and nor is this area. So we're assuming that a 4 million year prescription is consistent with that. And then finally, our apatite helium ages are more or less bounded by our 4 million year bracket here as well. Finally, we will prescribe a fault friction coefficient of 0.2, which is consistent with reduced frictional strength along the San Andreas fault modeled elsewhere. We start with our null hypothesis, where we assume that a linear elastic rheology. We prescribe a Young's modulus of 30 GPa and a Poisson's ratio of 0.25. And when we model this scenario through time, we see that the crustal thickening predicted by this elastic model, deflects the fault trace into something that is not particularly observed in our case. And also the crustal thickening magnitudes are nowhere near the quantities of minimum rock uplift that we observe. And that kind of underscores, or at least suggests, that this preliminary assessment of the elastic model may not withstand our observational check. We then move to our secondary hypothesis, in which we augment linear elasticity within a linear Drucker-Prager yield criterion to predict plastic failure. And the Drucker-Prager criterion is just a smooth approximation of the Moore-Coulomb surface. We prescribe different strain hardening curves to capture the asymmetric deformation in the Santa Cruz Mountains. Note that the Bay block, which is shown in the dashed line, strengthens strengthens more quickly than the Pacific block. And I should note that, that way. This model has a bunch of parameters that are self-prescribed. These aren't necessarily, well, I guess the initial strength of the rock is derived from the lithologies in the Santa Cruz Mountains, but all of these other parameters aim to capture the evolution of strength as evolution of the crustal strength as a bulk unit rather than individual rock units. So, subsidiary faults, among other things, and rheologic heterogeneities. There are a lot of parameters to play with here, notably what the original strength of each of the blocks is, where their strengths deviate, the slopes of each of these lines, where each of these strength plateaus or strength curves plateau. All of this is to say we have modeled a large portion of this parameter space. And while I don't pretend to suggest that our model is the unique and only solution, it is a small subset of models that actually works to produce the deformation that we observe.
Can I ask another question? Are
Of course.
those strain rates are prescribed? In other words, the hardening that you get when the strain rate is prescribed for the faults over the
Yeah, so these curves, other than I'd say the initial cohesion, which is justified in terms of lithologies present, these are prescribed. And I have reasoning for why that may happen. And I've got some subsidiary slides after the main talk, which I'd be happy to work through. But the short answer is there's kind of broad regional faulting in the Pacific block. And in the Bay block, there are a sequence of regional thrusts. And we suggest that the rotation of these regional thrusts out of favorable planes of motion as that thrust belt propagates outward may actually harden the crust as a bulk unit there.
Can I ask one more question?
Of course.
So the coefficient of friction, is that a constant or it has a rate dependency or even more higher order dependencies? Because the other question is, do you see the fault, the movement across the fault during a simulation, or the fault is always held fixed together, contact in each other with each other?
So in this case, this is it for this long-term model. This is actually a creeping fault with a constant coefficient of friction of 0.2. We'll show in our seismic cycle models, we play with that frictional coefficient to lock the fault and then unlock it for our seismic cycle modeling. But exploring the effects of static and kinematic coefficients of friction is an avenue of work that could expand on top of this, such that you can actually generate individual earthquakes of non-dictated size as the model evolves. With respect to the fault geometry is permitted to open, and it also evolves through time as deformation accrues in surrounding crust. And we will see that, if that answered your question, we'll see that in this following animation. Actually, we'll see the evolution of that fault geometry in 2D at least.
So I guess you partially answered the question. So you think the fault is creeping all the time during the simulation, right? The fault
during this simulation, yeah, it's creeping, and then we'll model stick slip behavior at a future point in the talk.
Got it. Thank you.
Yeah, no worries. Did you have a question?
The coefficient of friction is constant along strike?
It's constant along strike, yeah.
It doesn't make any.
I haven't prescribed any. I mean, you could prescribe different contact surfaces in the model to try and capture the effect of different areas of increased frictional strength. I haven't gone through that yet, but it would be an interesting study. So if we watch this model evolve through time, before we'll play this, I just want to note that tectonic thickening, this is the elastoplastic model, is in the top left. Thickening rate is the top right. Plastic strain is the bottom left, and strain hardening of that strain hardening Drucker-Prager model is in the bottom right. And when we play that through, we'll see that strain hardening evolves as a function of plastic strain, that the thickening rate varies over time and isolates as strain hardening evolves, and importantly, that this locus of plastic strain here down at the bottom of the model seems to dictate the thickening, the localization of thickening rate in the top of the model. Time in this animation is counting down from 4 million years to 0 million years, which is present day. All right. Next. So we now have a thickening model for the Santa Cruz Mountains. What do we do with it, and how do we transform it into the metrics of deformation that we observe? We'll now couple our tectonics and Earth surface processes. So if we first take this thickening model and we extract a long fault uplift and advection histories along the fault to reconstruct thickening histories for each node along the San Andreas. What that looks like is something like this. So if we pick our little node here, this is just as an example in this red dot, and we play that through time, we'll see that crustal thickening in that bottom left plot will evolve through time as that point enters and uplifts within the restraining bend. And then as that point exits the restraining bend, tectonic thickening will plateau. Ooh. I promise these animations are playing a little bit better on my computer, but I realize it doesn't help you, so I apologize for that. Now, if we take that thickening model and we couple it with a stream power erosional model in conjunction with a change in elevation modeled by rock uplift minus erosion, we observe that our three key inputs for this problem, where tau is the tectonic thickening rate, K is the erodibility, which we which we explore values ranging from that of a weak mudstone to a granite, and F is the ratio of a combined flexural isostatic deflection to a pure airy isostatic crustal response. We observe the following properties for a particular modeled catchment here, and these stream model catchments that I'm about to show you represent stream, come on arrow, catch up, there we go, represent the evolution of stream profiles that evolve parallel to the, or pardon me, perpendicular to the San Andreas Fault. And that looks something like this. So in a similar setup, we'll still have tectonic thickening here. We will have tectonic thickening in addition to rock uplift, exhumation, relief, and mean catchment elevation shown in this bottom plot. We'll have the evolution of that stream profile shown in the top right, and we'll have the evolution of the geothermal gradient of this particular crustal parcel in response to the exhumation in this catchment evolve through time. And if we play that forward, we see that as tectonic thickening increases, this stream catchment profile increases in elevation. And then as that tectonic thickening and associated rock uplift decay, erosion starts to take over and that basin lowers. So if we just play that through one more time, we'll see that tectonic thickening evolved, as do rock uplift and crest elevation or relief in this bottom plot. And then again, as tectonic thickening starts to plateau, erosion takes hold and that relief of that catchment model decays through time. This is a stream power erosion model here. So it's not as complicated as some of the state-of-the-art models for how these processes work, but it is linear and it works within our model framework. So that model was for one particular catchment model in our hypothetical, or in the Santa Cruz Mountains at one location. So you can imagine that if we run several catchment models, or even an infinite number of catchment models along the length of the San Andreas Fault, we'll produce these metrics for each position along the San Andreas and directly compare them to our profile predictions that we outlined earlier. So stepping through these, we have rock uplift, which we just extract the rock uplift at present day. We have uranium, thorium, helium measurements, for which we'll just couple the exhumational curve with that evolving geothermal gradient that we saw to construct a time temperature path, which then we can use to predict an apatite uranium, thorium, helium age. For relief, we just extract the top elevation and the bottom elevation of our stream catchment model. And for erosion rates, we calculate the catchment averaged erosion rates at present day, which is going to give us a metric consistent with that observed in the beryllium-10 erosion rate record. Finally, to compare horizontal interseismic surface velocities, we model an interseismic cycle by locking the San Andreas Fault and prescribing velocities at the far field and along the model base in the bottom of the fault here to produce that interseismic elastic bending. I'll describe this process a little bit more in detail in a few slides. We couple that velocity with velocities that result from other faults in the San Francisco Bay Area, and we interpolate those velocities onto the Bayview network of GPS stations for direct comparisons with velocities in the Santa Cruz Mountains. So with all of that and the framework to actually compare these predictions to our observations, let's walk through and see how each of our hypotheses do. In this comparison, the seismic or the elastic seismic cycle will be in blue, and the elastoplastic model will be in red. So for a series of catchments along the San Andreas, we note that the blue elastic model underpredicts rock uplift, and the red elastoplastic model overpredicts rock uplift, though note that these are largely minimum values along that length, so this is permitted. The somewhat diagnostic apatite helium ages are generally reproduced by the elastoplastic model, whereas the elastic model barely even produces temperatures to which these observations are sensitive, meaning if these apatite grains don't respond until a temperature of roughly 40 to 80 degrees C, and the closure temperature associated with those grains is 70 degrees C. This model predicts that temperatures don't exceed or barely exceed 40 degrees C. And so these are minimum ages. These actually wouldn't be reset using the elastic thickening model at all. For relief, we observe that relief is overpredicted in the southern Santa Cruz Mountains and underpredicted in the northern Santa Cruz Mountains. Though note that the Black Mountain Bend, which is here, is actually a feature that we don't explicitly model in our finite element model here. That is to say that the underprediction of relief here might be assisted by the fact that we don't model this, and if we did, it might induce additional rock uplift and topographic relief in that range. And the same can be said for our erosion rates, where we fairly nicely predict erosion rates in the southern Santa Cruz Mountains here. They're underpredicted north of about 35 kilometers, and that is again consistent with the position of the Black Mountain Bend. We also observe with the interseismic velocity fields that the elastic and the elastoplastic models are not particularly different or diagnostic for horizontal surface velocities. So in conclusion, for this part of the talk, predicted quantities are broadly consistent with observations for the elastoplastic model. Misfit in relief and erosion rates beyond 35 kilometers may be associated to Black Mountain restraining bend structure. And finally, the horizontal interseismic surface velocities are dominated by elastic straining and provide little insight for long-term deformation. So the takeaways here, the elastoplastic model generally predicts deformation that is consistent with observations spanning 5 orders of magnitude in time and 7 orders of magnitude in space. And long-term records of deformation revealed in careful geologic studies must be considered to fully understand crustal deformation, given the insensitivity of some of the shorter timescales. How then, and when and where does plastic strain actually accumulate during the dominantly elastic earthquake cycle? And that'll be the next topic of the talk.
I have a question on this part. So
yeah, of course.
In the restraining band, it looks like it's propagating.
It is.
So in your initial conditions, is the dimension of that, the 2 points where it's bending, is that are they closer together, and is it evolving to the current geometry, or are you starting with the current geometry and you're moving it forward?
We initially started with the current geometry and moved it forward, and we noticed that the propagation of that bend in response to deformation gave us a fault trace that is inconsistent with what we observed. Given that initial observation, we started with a steeper bend, and then had that evolve through time.
Okay, and then the other question I have is, I don't know, maybe it's difficult. What caused the initial bend?
I have an animation for this and some supplementary slides, but just to quickly describe that. So plate reorganization occurred from 4 to 6 million years, and the Pillar-Cetos fault is assumed to be the former the plate bounding fault. With the reorganization of plate motions at that time, it's assumed that the peninsular section of the San Andreas fault actually cut through and abandoned that Pillar-Cetos strand, and then the Pillar-Cetos strand has subsequently been advected along the fault as the bend itself advects or moves through time, and as plate motions accrue across the fault.
Okay, good. Yeah, thank you.
There's some really interesting topics associated with like reduced slip rates through time and how those might tie to the geologic record, which I don't have time for today, but I would love to talk about afterwards if you're interested.
Are you implying that the bend was larger in the past and that it's trying to get bigger?
Interesting. Yeah. So as this deformation accrues, the bend does shallow over time. So the step over is the same, but the angle of that step over is more substantial in the beginning. And this actually has some interesting implications for the localization of that strain hardening, which seem to isolate uplift in the southern Santa Cruz Mountains. So if we model earthquake cycle deformation with this model framework, we first slip our deformed model for an additional 250 years at the prescribed displacement rate. And we extract the velocities associated with this increment along the model base and the lower, that is greater than 10 kilometer depth fault trace. We then model in an interseismic phase by frictionally locking the upper portion or greater or less than 10 kilometer depth of the fault, but just by increasing the frictional coefficient to 0.3 instead of 0.2. And we prescribe the velocities extracted in step 1 to the model base and lower fault surface for that 250-year interval, which is more or less the assumed recurrence interval for large earthquakes that rupture the length of the San Andreas. To model coseismic deformation then and resolve that displacement discontinuity across the fault, we hold the model boundaries, model base, and lower fault surface fixed, and then we reduce the friction again on that locked upper fault surface, which produces the lateral displacement discontinuity observed across the San Andreas in this graphic. So interestingly, uplift seems to localize along the San Andreas coseismically, though plastic strain that occurs during the coseismic phase is actually fairly minimal. Instead, plastic strain is more pronounced in the interseismic phase and develops specifically in the southern Santa Cruz Mountains, and uplift interseismically occurs diffusely about the bend tips. We'll note also that the seismic cycle uplift concentrates near that southern bend terminus.
This is the model, right?
This is the model, yeah. And we'll then observe, let's see, this is the evolution of earthquakes over 3 seismic cycles, and so we'll just play that video. And I guess what I want to emphasize with this is that earthquakes cause subsidence of the highest peaks in the range on either side of the San Andreas. And we actually observe this in the Loma Prieta quake, though there are distinct differences between this model and the Loma Prieta rupture model. And also, interseismic uplift is largely accumulates during the later stages of the interseismic period when stresses in the crust surrounding the San Andreas are highest. Also, uplift patterns over the 3 full fault rupturing earthquakes, at least consecutive earthquakes, mimic those observed for an individual earthquake. These might vary through time as the properties of the crust evolve. There are differences between the elastic model and the elastoplastic model. So the question might be, can you use observed vertical uplift fields to differentiate between these 2 rheological models? Unfortunately, the spatial extent of the observed interseismic uplift fields in the Santa Cruz Mountains is limited by permanent scatterers on that side of the fault. And it's also highly vegetated, high relief, and there are also seasonal fluctuations that complicate this measurement. Additionally, viscoelastic relaxation and afterslip associated with the Loma Prieta fault complicate this picture, and so we can't actually really resolve these velocities and compare them to our modeled quantities. However, the long-term deformation seems to dictate earthquake cycle uplift, in that strain hardening in the Bay Block, associated with this locus of hardening right here, seems to localize deformation in the Pacific Block here in the southern portion of the Santa Cruz Mountains. This seems required to explain the high erosion rates noted in the southern Santa Cruz Mountains and the young apatite uranium thorium helium ages. Finally, the predicted uplift and plastic strain distributions during the earthquake cycle may actually serve to influence seismic hazard assessments if you know where uplift and plastic strain might be most likely to occur during these seismic cycle phases. That is to say, material state of Earth's crust appears to strongly influence the distribution of earthquake cycle deformation. And again, we might then ask, how does the geologic history, lithotectonic heterogeneity, and faulting impact the localization of deformation? There are a series of related studies in future directions which we can explore. We are just about at the time where we might want to answer questions. So I'm happy to go through this next section if we'd like, or answer questions. I don't want to keep you guys too far over time.
You're the boss of the seminar.
Why don't you finish your talk?
Okay, yeah.
Ask him how many slides first.
How many slides?
There are 3 slides with builders in between.
Okay,
So
this should work.
So many of the models for Santa Cruz Mountains range evolution are fairly simplistic models. However, the geologic history and structure of the Santa Cruz Mountains is demonstrably complex, with notable changes in geology across faults and complex arrangements of lithotectonic terrains. I'll lump our model in somewhere in the middle between these 2 categories, where it's still a continuum model modeled with finite elements that lack discrete faults, but we also fail to incorporate a lot of the complexity that we observe in the actual rock record. Notably, across the San Andreas Fault across the Zayante Fault, this regional structure, the Ben Lomond block here hosts shallow selenian basement, which is a coherent granite, thinly mantled by less than 1 kilometer of sediments, generally on the order of 100 meters. Directly across that fault, we have a 5+ kilometer thick sedimentary sequence, under which we only geophysically infer the presence of crystalline basement. And what that actually looks like in this graphic, which is highlighted in this little red square here, is that these granites noted here in pink are juxtaposed just across this fault against lithotectonic terrain with very different integrated crustal strengths. And so that might influence the localization of strain and deformation between these 2 blocks. Some undergrads that I've worked with at Stanford as interns, and I have measured numerous apatite, uranium, thorium, helium ages and constructed these sections. And we note that helium ages are typically very young in the La Honda block, which suggests that exhumation in that block is much more extensive than we observe in the Ben Lomond block. And that's just to say that over large geologic timescales, the localization of strain in this more compliant block, where this is just a cross-section from A to A prime, is observed in our exhumational studies and even in our reconstructions of the geologic record, where this normally flat-lying unit in the granitic terrain is actually bent and upwarped and projected up and over this severely folded terrain in the eastern portion of this section. The role of faulting in the Santa Cruz Mountains is important as well. We don't consider faults in our model because it's a continuum model, but we try to get at this with our strain hardening prescriptions. That is, the difference in strain hardening across the fault. However, fault geometry specifications in our finite element model are somewhat prohibitive for a number of reasons. And the question is, how can we separate distributed failure that we predict from crustal deformation accommodated along discrete slip-along faults? Some colleagues of mine use boundary element models and geomorphic metrics to invert for long-term slip rates along far-field slip rates, and then resolve these onto existing fault structures to deduce seismic hazard along regional faults in the Santa Cruz Mountains. And a colleague of mine, Stefan Garcia, uses discrete element models to model non-prescribed fault generation in a 3D sense. So these allow for faults to propagate naturally without pre-specification. A finite element model, in contrast, requires prescribed contact surface geometries and faults which evolve, but also require a pre-prescribed geometry. And the question is, will a DEM model that captures the evolution of the Santa Cruz Mountains capture the role of regional faulting? Stefan and I intend to collaborate on this in the coming years, and we'll be excited to report on those when those results come in. So with that, we've answered our 3 original research questions, and I would like to thank you all for your time and attention, and I would be happy to take any additional questions that you might have.
Yes, I do have a question.
Yeah, Chi, go ahead.
All right. Have you compared the measured stress direction with what you have modeled?
I have not, and that's actually a wonderful suggestion. Because I think that would be actually somewhat, that would be interesting to explore and potentially somewhat diagnostic for the, reasonability of our model.
Yes, you remember one of your colleagues, Mark Sobak, has made a famous discovery that the stresses along the Seniors Fault are normal to this fault.
Right.
And so that should be a strong constraint to your model.
Duly noted, the tectonic models in Abacus obviously have records of stress, and I will be sure to check those in the coming days, just from a curiosity perspective.
Okay.
So let's thank Curtis again.
Awesome.